Welcome to the first part of my in-depth series about the PC mainboard. In this multi-part videos, I will explain in a step-by-step process how a modern computer mainboard boots up. From essential components like the chipset, the power phases, the VRMs, the RAM memory, the CPU and the RTC circuit, this series will empower you to truly understand how a motherboard works. By the end of this course, you will be equipped with enough knowledge to analyze and repair any mainboard like a professional. In today's episode, I will focus on the motherboard form factor, the chipset, the CPU socket and the RAM memory. If you gained any value from this guide, consider giving it a like. It will help me to grow the channel and create more content that you enjoy. And do not forget to subscribe to the channel for more in-depth analysis like this one. So, let's start. The physical size of the mainboard plays a role in determining how the components are arranged on the mainboard. Here are the four most commonly used standards. So we have the extended ATX, the ATX itself, micro ATX and the mini ITX. And as you can see, this is a really large mainboard, and the ATX is the most commonly used mainboard for desktop PCs. Then we have the micro ATX and the mini ITX. So these two mainboards are mainly used for small builds. The extended ATX is larger than the ATX itself. This mainboard is designed for high-end workstations or enthusiast builds. You can also connect multiple GPUs or high-performance components because you have more expandability. So this mainboard fits only in specially designed larger cases. So the dimension of this mainboard is 12 by 13 inches. This mainboard is the ATX mainboard, and ATX stands for Advanced Technology Extended. The dimension of this mainboard is 12 by 9.6 inches. This mainboard is the most widely used form factor in desktop computers. It provides enough space for multiple PCIe devices. There's also space for enough RAM memory. You have 4 slots here. The micro ITX or MATX. The dimension of this mainboard is 9.6 by 9.6 inches. This micro ATX is a little bit smaller than the ATX itself. This mainboard has a fewer expansion slots. This mainboard fits in the most computer cases because most computer cases will support the ATX format and also the micro ATX format. The smallest mainboard is the mini ITX. It's 6.7 by 6.7 inches. It is popular in small form factor builds. This mainboard typically includes 2 slots for the DDR memory and 1 slot for the graphic card. If you compare all these boards with each other, you see that the placement of the components is most of the time at the same location. At the backside you have your hardware connectivity, you have the CPU socket that is located in the middle of the board, and near the CPU socket there will be some RAM slots. So in the extended ATX board you have 8 slots, and in the normal ATX form factor you have 4 slots. The PCIe slots are located at the back end. Then you have the chipset. The chipset plays a role in the physical layout and organization of the component on this mainboard. It acts like a central hub for communication between the CPU and other hardware devices. All those mainboards have the same 24-pin ATX connector and also a CPU connector. The chipset manages the communication between the CPU, the random access memory, storage drives, hardware devices. The chipset determines how quickly and efficiently the data moves across the system. The chipset determines the number of PCIe lanes available, affecting how many GPUs, SSD and other expansion cards a user can install. So a high-end chipset supports more lanes and then therefore more expansion possibilities. Modern chipset also comes with an integrated security features like the support for secure boot, hardware-based encryption and trusted platform modules, the TPMs, which are critical for protecting sensitive data and enabling security-focused functions in a modern operating system. In older generation motherboards, you had a North Bridge IC and a South Bridge IC. So instead of one chipset, there were two chips. The first IC was called a North Bridge and it was located near the CPU, and it handled the CPU, RAM and GPU communication. The second chip was called the South Bridge, and the South Bridge handled all the low speed communication and also the communication with the hardware devices. In the modern generation motherboards, the North Bridge and the South Bridge are combined into one chip that is called the PCH. If you want to connect an internal graphical card, please be aware that you put it in the correct PCIe slot, because we have low speed PCIe slots and also high speed PCIe slots. The difference is the low speed PCIe slot most of the times are connected to the chipset, so there are less data lanes available for this slot, and that is why the speed is lower, and also the data goes through the chipset and then to the CPU. If you want to connect a graphical card, you have to connect it to the high speed data lanes that are connected to the CPU, because you want to run it at full speed. The same is for the M.2 slots. Some of the slots are connected to the chipset and they work with a lower speed. And there are some M.2 slots that are connected directly to the CPU, and that will use the full speed. So please be aware where you connect your SSD and your graphical card. The evolution from the traditional North Bridge and South Bridge design to the platform controller hub chip represents a significant shift in how motherboards manage data flow and component communication. The North Bridge was a critical chip that connected the CPU to the high-speed components like the RAM and the graphics card. It handled the most data-intensive tasks and acted as a bridge between the CPU and those fast components. The South Bridge was responsible for the slow speed connections, like the storage drives, USB ports, audio and network interfaces. This two-part system, the North Bridge and the South Bridge, helped balance the data flow, with the North Bridge handling the high-speed connections and the South Bridge handles the low-speed connections. As the CPU technology grew, processors started to integrate more capabilities directly on the CPU die. For instance, Intel and AMD began embedding the memory controller and the PCIe controller directly into the CPU itself. This reduced the need for a separate North Bridge chip, as the CPU could now handle high-speed data tasks internally, improving the performance and reducing the latency between the CPU and these components. With the memory and the PCIe controllers now inside of this CPU, Intel and AMD streamlined the motherboard design by combining the functions of the North Bridge and the South Bridge into a single chip, and that is called the Platform Controller Hub, the PCH chip, and the PCH is now the chipset. So these two chips are converted into one chip. The PCH now serves as a central hub that handles all remaining tasks. It connects slower components like the storage devices, USB ports, network controllers and audio. This makes the motherboard layout simpler and allows for faster communication between those components. In short, the evolution to a PCH design reflects the shift towards integrating more capabilities directly into the CPU, making motherboards more efficient and faster by eliminating the need for a separate North and South Bridge. So the PCH handles everything else that the CPU doesn't need to manage directly. This is an example of an Intel motherboard that supports the Intel Core i7, i5 and i3. These CPUs are from the first generation. So for this sheet I used the x85 chipset as an example. And here you can see the North Bridge and the South Bridge. All the low speed peripherals or the low speed connectors, the back end connectors, all those data will go to the South Bridge. And the North Bridge will handle the high speed communication between the random access memory and the PCIe slot with the CPU. This is the RTC circuit. This is the 24-pin ATX power connector. This is the CPU power. It is a Super I/O chip. So this handles the data signals from the buttons, the reset buttons, the keyboard signals. So also the low speed signals, it will go to the South Bridge. From the South Bridge, it will go to the CPU or the North Bridge. If you have a lot of peripherals that you want to connect on your computer, You need a higher chipset because it will have more connectivity for all those devices. This is a second generation motherboard that supports the Intel processor Core i7, i5 and i3. This mainboard implements the H76 chipset. So this is a chipset for the mainstream. When the Intel CPU supports the integrated GPU, then CPU will generate an image and this image will be sent to your monitor. So this is a good example where you can see how the chipset is implemented on the motherboard. So this chipset integrates 4 SATA connectors with a speed of 3 GB and also 2 SATA connectors that integrate 6 GB. So the speed is 3 and 6 GB. So in total we have 6 SATA connectors, and those 6 connectors you can find on the mainboard. This chipset also supports dual BIOS. If you look at the mainboard, there is a master BIOS and a backup BIOS. When the CPU supports integrated GPU, then the signal will be sent to the chipset, and from here it will go to your monitor. This PCIe slot supports 16 lanes of data, and that is connected to the CPU. So this PCIe slot will communicate with your CPU. Then we have a PCIe slot with 4 data lanes and 2 slots with 1 data lane. So if you look at the mainboard, these are the 2 PCIe slots with 1 data lane, and this is the one with 4 data lanes. And those slots will communicate with the chipset and from there with the CPU. Also the audio and the LAN connectivity. So these two will go, according to this image, to the chipset. Also the SATA data lines will go to the chipset. The PCIe slots with 1 data lanes will go to the chipset. The PCIe Express with 4 data lanes will also go to the chipset. The BIOS clock signal and data will go to the chipset, according to this image. But the DDR3 memory, according to this image, will communicate directly to the CPU. And also this slot with 16 lanes will communicate with the CPU. According to this chipset, the chipset supports 14 USB 2.0 ports. So if you look at the motherboard, here's 1, 2, 3 and 4, 5. So depending on the use case of the motherboard, it can implement a maximum of 14 USB ports. This is Super I/O chip. So the COM ports and the mouse is connected to this chip. This chip communicates with the chipset by a LPC bus. I think it is a low pin count bus. And if you look at the mainboard, you can see that the Super I/O is implemented here. So the mouse connector and the COM ports are connected to this Super I/O. This Super I/O will communicate with the chipset, and from the chipset it will go to the CPU. If you compare the second generation Intel motherboards with the first generation Intel motherboards, the second generation has more support for more PCIe lanes, overclocking, and it supports integrated graphics for the CPU. So let's say we have one PCIe Express slot of 4 data lanes and 2 with 1 data lane. If you compare it with the first generation, we can see that the first generation chipset supports 6 PCIe Express slots, but only with 1 data lane. In the second generation, we have 2 PCIe Express that supports 1 data lane and 1 with 4 data lanes. So that is an increasing support for the PCIe lanes. This is the third generation of the Intel motherboard. It supports the third generation of the Core i7, i5 and i3. So in this image you can see the H77 Express chipset. This mainboard is not very different as the previous one. So we can see that this is a CPU part, this is the real-time clock part, this is the Super I/O, this is the audio part, and this is the chipset because we can see the heatsink, 24-pin ATX power connector, CPU power connector. These are the VRMs. They're located near the CPU, and these are the power regulators that belongs to the RAM slots. This is the audio part, and you can recognize an audio part by the audio chip and also the capacitors near this audio chip. The chipset for this third generation motherboard has an increased support for the PCIe lanes. It supports overclocking, and the CPU can have integrated graphics. If you look at the image for the H77 chipset, we can see an increased functionality on the PCIe Express slot, so you can have up to 8 PCIe Express slots. You can have 6 SATA ports. You can have 3 independent display supports, and this chipset also supports 4 USB 3.0 ports and 10 USB 2.0 ports. So again, these are the maximum functionality, but every motherboard can implement a subset of those requirements. So instead of 4 USB 3.0 ports, the motherboard can implement 1 or 2 of those ports. So it really depends on the manufacturer how it implements the chipset. This is a 4th generation motherboard that supports different chipsets. So this chipset implements these functionalities. But if you look at the physical layout of the motherboard, the location is still the same. So these are the back end connectors. These are the PCIe 3.0 slot. So this is the high speed slot that will go to the CPU. Then we have the lower speed slots. Here is the USB located, the 6 GB SATA port. So if you look at the chipset, you can see that it supports 6 SATA ports of 6 GB, and that is implemented on the motherboard. This is the front USB 3.0 header. So if you look at the chipset diagram, it supports up to 6 USB 3.0 ports. So this is one of those ports, and the other one are located here. Then we have the LAN connectivity, and according to the image, it will communicate to the chipset, so the data will go to the chipset and from there to the CPU. This is the audio part, and the audio part will communicate with the chipset. So it's the same story. The chipset defines how the communication goes, and if you're gonna analyze the motherboard, it will help you to troubleshoot the problem. So if there is any audio problems, then you know, hey, this communicates with the chipset. I can investigate this part and maybe chipset part, but the problem will not be the CPU. So these are the DDR3 slots for RAM memory, and according to the image, it communicates with the CPU. So the data lines will go straight to the CPU socket. This is a 5th generation motherboard, and again, it supports different chipsets. The processor supports integrated graphics. So if it is implemented, you can use the display ports. So the data of this display port comes from the CPU part. So the chipset is implemented underneath this heatsink. This is the BIOS. This is the Super I/O chip. This is the audio part. So again, this is the audio chip in combination with 2 capacitors. And the sound data comes from the chipset. This is a 24-pin power connector. This is the CPU power connector. Next to the CPU, you can find the voltage regulator that will supply the power for the CPU core. This is the RTC circuit. This is probably the high-speed PCIe slot that will communicate with the CPU. So the layout of this motherboard is still the same. The only difference is that the hardware devices or the hardware implemented on the mainboard is different. It can have different technology, like different data lanes and higher protocol or something like that. So physically, it's still the same motherboard. This is a 6th or 7th generation Intel motherboard. These are the different chipsets. So the H1110 is the entry-level chipset up to the Z170. So this is a high-end chipset that supports overclocking. If you compare this motherboard with the previous motherboard, the 6th and 7th generation implements the DDR4 technology. So the DDR now works on DDR4. So the chipset is located under the heatsink. We have the audio part, so this is high-end audio circuit. We have some crystals that will generate a clock signal. These are the back-end connectors. 24-pin ATX connector, CPU connector. So this PCIe slot is the high-speed slot for the graphics card. This main board also supports the postcode. So So if the board starts up, you will see the postcode on those two LED displays. This motherboard is an 8th or 9th generation Intel motherboard. These are the different chipset that it supports. In this case, it's the Z370. And also this is a high-end chipset, also supports overclocking. And again, the layout is almost the same again. So we have the CPU part, we have the voltage regulators, RAM memory slots, the chipset underneath a heatsink, M.2 slots, PCIe slots. So the first one will be probably the high speed part, and it will go to the CPU part. This will probably be the audio part, because we have an audio chip and some capacitors. This is the RTC part, and this is probably the Super I/O. So the physical layout is still the same. Maybe some small components are located on a different area, but in the whole, it's still the same motherboard physically. This is a 10th and 11th generation Intel motherboard. In this case, it's the H470. It's a mainstream chipset. So this is the image of this chipset. We can now see how this technology is implemented, how the communication flow goes, and that is translated into a motherboard. We can identify the CPU part, the voltage regulator part, the RAM slot, the voltage regulators that will create voltages for the RAM, the back-end connectors, Super I/O chip, audio chip, M.2 slots, PCIe slots, the chipset that is under a heatsink, audio connectors, RGB connectors. Again, the physical layout is almost the same. The 12, 13 or higher generation Intel motherboards implements DDR5, so the memory now works on DDR5. The DDR5 memory is physically a little bit different than the DDR4 layout, but again, the chipset now supports DDR5 and also PCIe 5.0, but physically it's still the same. We have the CPU, we have the VRMs, the RAM slots, 24-pin ATX power connector, the CPU power connector, we have the back-end connectors, we have the audio part, the M.2 part, the PCIe slot, the chipset underneath a heatsink. Physically, it's still the same motherboard, so that will make it easier to identify the components, and that makes it easier to troubleshoot. Now I am going to look at the AMD motherboard. So this motherboard supports the AM3 socket. For AMD CPUs there are different chipsets, and these chipsets are specially designed to use for AMD processors. So if you look at the mainboard, the location of the most important components is still the same. So we have the back-end connectors, PCIe slots, SATA connectors, front panel connectors, audio circuit. Close to the CPU you have the VRMs. Because this is an old generation motherboard for AMD, there's a north bridge and a south bridge. So I think the north bridge is located under this heatsink, and this will be the south bridge. Physically, it's still the same layout. This is an AMD 990FX chipset, and as you can see here, we have the north bridge and the south bridge. North bridge, south bridge. This chipset supports DDR3 memory. So as you can see, the physical placement of the components, the layout is still the same if you compare it to an Intel motherboard. So this chipset here supports DDR4, and if you look at the chipset diagram, it will communicate with the CPU. If you look at the audio section, you can see there is something different here. This audio circuit communicates with the CPU. And if you look at the mainboard, it's still the same. So if your back-end connects again, your CPU, voltage regulators, the DDR slot, 24-pin power connector, PCIe slots, M.2 slots. This is the chipset, and it is located underneath this heatsink. This is the audio section, and as you can see here, it's an audio chip with a lot of capacitors. This is how you can identify it. This AMD motherboard is one of the latest generations, so it supports DDR5 memory. And in this picture you can see this is the AM5 processor. This is the AM5 chipset, and as you can see, the chipset communicates with the NVMe drives, the LAN controller, Wi-Fi module, card reader, USB ports, optical drives, hard disks. So all the communication is between those devices with the chipset and the CPU. The CPU itself has a PCIe controller built in and also a memory controller because it will interact with the DDR5 memory. The audio circuit communicates with the CPU, and also if you update the BIOS by USB, this data communication goes to the CPU. If you compare this AMD board with the older version of AMD boards, also with the older version of the Intel boards, it's still the same. The location of the most important components are here. So the back-end connectors, the CPU socket, DDR slots, 24-pin ATX power connector, the chipset underneath this heatsink, M.2 drives underneath this heatsink, PCIe slots, the audio circuit, and the CPU power connector. So for us, the physical layout is the same, and that will make it easier to pinpoint the components and how it should behave for analyzing and troubleshooting purposes. When you compare an AMD CPU with an Intel CPU, there is a difference. The AMD CPUs had pins on it, and the Intel CPUs doesn't have pins but pads. With the newest CPU, AMD moved from CPUs with pins to CPUs with pads. Here you can see an AM4 socket and an AM5 socket. So in the latest CPUs from AMD, the CPU supports the AM5 socket, and the older generation supports the AM4 or AM3 sockets. And as you can see here in this socket, there are holes, and the pins from the CPU will go into those holes, and then you can secure it with a retention mechanism. So in the AM5 sockets, you can see all those delicate pins, and these pins will make contact with the CPU. In an LGA socket, the pins are on the motherboard, so these are the pins, and not on the CPU itself. The CPU itself has small flat contact pads on its underside that correspond to the pins on the socket. When you place the CPU onto the socket, the pins make contact with these pads, and a retention mechanism secures the CPU in place. And this is an LGA socket from Intel. So you have LGA, it stands for Land Grid Array, and the number here gives the number of pins available in the socket. The AMD or the Intel processor needs power to operate. VCore or voltage core refers to the core voltage that is supplied to the CPU in a computer. It is one of the most important voltages in the CPU operation. VCore is the power supply for the CPU. It provides the electrical power needed to drive the CPU's internal transistors and circuits. These circuits perform tasks such as executing instructions, managing data, and processing signals. The VCore is closely linked to the CPU's operating frequency, also known as the clock speed. A higher VCore allows the CPU to run at higher clock speeds, improving the performance. When users overclock their CPU by increasing its clock speed beyond the manufacturer's rated frequency, they often need to increase the VCore voltage to maintain a stability at the higher frequency. Without sufficient VCore, the CPU may become unstable, leading to crashes or errors. This VCore voltage can be manipulated in the BIOS settings. So depending on the motherboard that you have, if the chipset supports overclocking, then you can change the VCore voltages. So by increasing the VCore, also increase the amounts of heat that is generated by the CPU. Therefore, higher VCore settings usually require better cooling solutions to keep the CPU within the safe temperature limits. For modern AMD or Intel CPUs, the VCore usually ranges from 0.7 volts up to 1.5 volt depending on how you overclock the VCore. You also have some additional voltage rails for the CPU. One of them is the SA voltage, so you can also see it in the BIOS setting. So the system agent is responsible for managing the different input-output tasks, including the memory controller. The memory controller is responsible for managing the data flow between the CPU and the system RAM. The SA voltage helps to stabilize the memory controller and ensures that the memory-related operations such as data transfer and timing run reliable. The default system agent voltage is typically around 0.9 volts up to 1.2 volts, but this can be different depending on the processor model and also the motherboard. You also have the input-output voltage. So the input-output voltage in a CPU powers the input-output circuits that is responsible for communication between the CPU and external devices such as RAM, storage and other peripherals. Proper input-output voltage is important, especially in overclocking scenarios. The default voltage is typically around 1 to 1.2 volt. This can depend on the specific CPU model and motherboard. When you measure the VRM voltage, it should be between the 0.7 up to 1.5 volt, depending on your BIOS settings. In this list you can see the AMD processors, so from socket AM4 up to AM5. The VCore voltage is typically around 1.1 volt up to 1.4, maybe 1.5 volt, depending on how it is set up in your BIOS, if you can overclock it. Do not remember this list, but just remember it has to be around 0.7 up to 1.5 volt if you want to measure the VRMs. Random access memory is used in the mainboard of a computer because it serves as the primary volatile memory that allows for fast temporary storage and retrieval of data that the CPU actively uses during its operations. The mainboard provides the necessary slots for installing the RAM modules. RAM is used by the CPU to store data and instructions that are actively being processed. When you open a program or load data, it is loaded into the RAM, because it can be accessed much faster than data stored on slower storage devices like hard drives or SSDs. The CPU constantly fetches data from the RAM to execute programs, to perform calculation, and also to process the information. The faster the RAM, the quicker the CPU can access the data it needs, improving the overall system performance. RAM is volatile, meaning it loses all its stored data when the power is turned off. This makes it suitable for temporary storage while the system is running. Unlike hard drives or SSD that provide long-term storage, RAM's volatility makes it ideal for tasks that require high-speed access and don't need to be retained after a system shutdown. The more RAM you have, the more applications and data can be stored temporarily, allowing for smoother multitasking and preventing system slowdowns when multiple processes are being executed at once. The memory control manages the data flow between the CPU and the RAM. The motherboard's role is to ensure that the correct data is transferred efficiently. The memory controller is embedded into the CPU. Some CPUs come with an integrated GPU, and in such cases, a portion of this RAM memory that is located in this RAM is used as video memory. This allows the CPU to share memory resources with the integrated graphics unit, which is critical in systems that do not have a dedicated graphics card. This is a DDR4 memory module, and these are the memory chips, and this is the front side. So at the first pin, this is called pin 1, and the last pin is pin 144. The notch is located at the second row at the front side. This is the back side of the DDR4 memory module. Pin number 288 is located here, and the notch is ending at the first row at the back side. The pin on the right side starts with 145. Keep an eye on the notch, then you know how to count the pins. In this table you can find the most important pins that are located on the DDR4 memory. For the power, the VDD power is 1.2 volt, and that's the main power supply. The VPP pins are located at these pin numbers, and the VPP is also called voltage pumped. It has a voltage level of 2.5 volt. So this power rail helps to turn on specific row, also called a word line, so the data can be accessed from that part of the memory. Inside each RAM chip there are rows and columns of tiny cells that store data. The voltage pump 2.5 volt helps to turn on a specific row called the word line, so the data can be accessed from that part of the memory. This voltage is different than the voltage of the VDD power, because the VDD power uses 1.2 volt and the voltage pumped uses 2.5 volt. So VPP helps with a specific job inside of the memory that make it run better. Then we have VTT termination voltage. It's a voltage level of 0.6 volt. It's located at pin number 77 and 221. So VTT is used to properly terminate the signals on the data lines, so the data lines of the DQ and DQS, to avoid signal reflections and ensure clean data transmission between the memory controller and the DRAM chips. The voltage of the VTT is determined by the VDD power and divided by 2. So 1.2 divided by 2 is 0.6 volt. That's how you can calculate the termination voltage. Then we have the VDD SPD, also known as a serial presence detect. It has a voltage between the 2.5 volt and 3.3 volt, and it is located at pin number 284. So this power supply will deliver power to the EEPROM that is located inside of the DDR4 memory module. On pin 141 and 285 we have the serial communication, so this is the clock signal and this is the data signals. Then we have the VREF-CA, also known as the reference voltage for the command and address. It has a voltage of 0.6 volt and is located at pin number 146. So the VREF-CA stands for reference voltage for command and address. It's a specific reference voltage used for signaling the command and address lines in the memory system. VREF-CA is typically set to the half of the VDD power, so 1.2 volt divided by 2 is 0.6 volt. So it's the same principle as the VTT termination voltage, also at 0.6 volt. The reference voltage CA is generated for each memory channel. If the memory works in channel 1 and not in the other channel, check this voltage 0.6 volt if it is present in the channel 1 and channel 2. That can explain why the memory works in channel 1 but not in channel 2. This is a top view of the memory slot, and at pin 146 you can find the reference voltage of 0.6 volt and the resistance is higher than 1 mega ohm. Pin 288 is located here. It's called VPP 2.5 volt and the resistance is higher than 1 mega ohm. On pin 284 you can find the VDD SPD. It's between 2.2 volt and 3.6 volts and it's also higher than 10 mega ohms. VDD is located at pin 76. It's 1.2 volts and the resistance is higher than 500 ohms. And the VTT is located here on pin 77. It's 0.6 volt and the resistance is higher than 80 kilo ohms. So this is the top view of a RAM slot. Pin 1 is located here and pin 2 is located on the upper side. You count it as 1, 2 and then 3 is below and 4 is up again, and that is how you count it. So pin 144 is the last pin located here. And on the back side pin 288 is located, and if you count it back you get pin 146. This is the DDR5 memory module. One of the most notable changes in DDR5 compared to DDR4 is the introduction of the PMIC. The power management integrated circuit is now integrated on the memory module itself. The power management chip is a small chip that is located on a DDR5 DIMM. This power management IC will generate different voltages that is needed to operate this DDR5 memory. In DDR5 there will be a power supply like 5 volt going to this module. The power management IC will use this voltage to generate different voltages like the VDD, VDDQ, VPP. If you compare it to the DDR4 voltages, the voltages for the DDR4 are generated on the motherboard. And in DDR5, these voltages are created on the module itself. The motherboards that support DDR5 provide power to the DDR5 DIMM, but offloads much of its power regulation to this PMIC. Also, shifting the voltage regulation to the DIMM reduces the motherboard complexity, allowing more straightforward power delivery designs, so the motherboard is less complex. And when this power management IC fails, it will only impact the module itself, so you can swap this DDR5 memory with another one and it will work again, instead of having this voltage regulation on the motherboard. Because if it fails on the motherboard, all the modules are impacted. The other changes are the module key. So in DDR5 the module key or notch is located here, and in DDR5 it's located on the left side. In DDR4 the resistors and capacitors are located near the connectors, and in DDR5 these resistors and capacitors are now surrounding the memory chip, and also the resistors are located near the notch. In this table you can find the most important signals and voltages. And as you can see, the voltage generation is now done on the module itself, because there are not dedicated pins for these voltages, but it is done on the module itself. On pin 4 and 5 you can find the serial communication of 1.8 volt, so the clock is 1.8 volt and the data is 1.8 volt. Then we have the voltage reference for the command and address, so it's 0.55 volt. And that is also being generated by the power management integrated circuit. On pin 1, 145 and 146, the VIN bulk is present. So this is the input power supply. So in this case it's 5 volt, and from this 5 volt all those voltages will be generated by this power management integrated circuit. On pin 147 we have the power good signal. The output of this power good signal comes from the power management chip. The power management chip will set this pin to high if the power generated on the module itself is okay. Then we have the enable signal on number 151. So when this pin is high, the power management IC turns on the regulators. And when this pin is low, the power management turns off the regulator. And the reset signal can be found on pin 95. This is the front view of the DDR5 memory, and as you can see this is pin 1. The notch is located on the right side, and this is pin 144. On the back side this is pin 145, and this is pin 288. In this video I have explained which factors are responsible for the physical size of a modern mainboard, which role the motherboard form factor, the CPU, the RAM and the chipset have when it comes to the location and implementation of the different components on this mainboard. By understanding how the chipset communicates with different components, you can narrow down the root cause of a problem and try to fix it. In the next videos, I will analyze how the standby and power on sequence works. For that I will use this 7th gen Intel motherboard. I will provide information about the BIOS, the voltage regulators, the ATX power supply, the Super I/O chip, the platform controller hub, also known as the chipset, the different voltage rails that are on the motherboard, how a logic AND gate chip works, the VRMs that generate the VCore voltage for the CPU. I will also provide information about the TPM headers and which tools you can use to troubleshoot a mainboard. If you gained any value from this video, consider giving it a like. It will help me to grow the channel and create more content that you enjoy. And do not forget to subscribe to the channel for more in-depth analysis like this one. Till next time, bye bye.